This is a general video on limits, its properties, types, and so forth. So, if you'd seen one of my previous videos, a limit is nothing but the value of a function at a given point as x approaches that point. So, to put things in perspective, let's take a piecewise defined function, x and f of x. Let's say I have a function of this sort. So that is a piecewise function, and let's say this is -1 and that's +1, we have 0. Let's say that is 4. So this is our piecewise function. Now, if we wanted to know the value of the function from algebra, it's quite obvious the value of the function at 2 is right there. It's well defined. This is f of 2, whatever that number might be. Let's call that to be 2, that to be 4, and that to be -1. It's quite obvious. And if I have 0, and if I wanted to know f of 0, the value would be right there. That is also obvious. That is f of 0, or the initial value. But if you observe the point at -1, or the value of the function, we're actually sort of confused. Is it that, or is it that? The closed dot implies the value of the function is -1. The closed dot here also implies the value of the function is actually 4. But where do limits come into play? What is the limiting value? Now, we typically write the limit of the function as some function limit as x approaches some number a, you get a value L. That L is the limit of function f of x as x approaches a. Now, if you have a point, you can approach the point from two sides. So you could either approach the point from the left side, so we could denote it as a minus f of x. Let's say we'll call that L1. This is the limit of function f of x as x approaches a from the left of a. Similarly, I could say x is approaching a from the right side. We denote it as a plus f of x. I'll call it L2. This would be the limit of function f of x as x approaches a from the right of a, or right side of a. By right I mean right side. So let's see, we have multiple breakpoints here. I have -1, I have 1, I have full. So let's say limit x approaches -1 from the negative side. So I'm going to approach -1 this way from the left hand side. So x is getting closer and closer to -1. So as x changes, the function changes in this manner. So as x gets closer and closer to -1, the function is getting closer and closer to that point. So at -1, when you come from the left hand side, you kind of hit that wall and you end up having -1. So the point that you hit first, as x approaches -1, the value of the function is -1. That is called the left-sided limit, or the left side limit of f of x. In a similar manner, I could approach 1 from the right side. So if I start from the right and I approach 1 from that side, the function is changing in that direction. So it is coming down. So as you get closer and closer to -1, the function's getting closer and closer in that direction, and it hits that open door. Now, the function does not take the value 2, but it's getting closer and closer to the value 2. So as you come from the right, the value of the function as you come from the right is +2. That's what we call the right side limit. An important note is if the left side limit and right side limit at a, at x, equals a, are the same, then the limit exists at x is equal to a. In other words, if L1 is equal to L2, which is equal to L, then limit x approaches a, f of x will be L. In other words, it exists. Now, if you look at the example that we have here, the left side limit is -1, the right side limit is +2. Clearly, -1 does not equal +2, which would imply the limit does not exist. Or DNE at x is equal to -1. Now, let's do another case. Let's do it for x is equal to 1. Let's approach 1 from the left hand side. So as I come from the left toward 1 in that direction, the function is going up toward that point. The function's moving that way and hits that wall, so limit from the left hand side at 1 would simply be 4. Now, if we get closer to 1 from the right hand side, the limit as you approach 1 from the right will be 2, because the point moves and gets closer and closer to 0, and that value is 2. Now, does the limit exist at 1? Clearly does not exist. And the last case, let's look at x approaching 4 from the left. So we are approaching 4 from the left hand side. X is getting closer and closer to 4. As x is getting closer to 4, the function is decreasing and it's hitting that value. Perhaps that's about 0.25 with a negative sign. So let's say that is negative 0.25. So the limit of the function as you approach 4 from the left hand side is negative 0.25. The limit of the function when you approach 4 from the positive side, in other words that way, as you get closer and closer to 4 from the right hand side, the function decreases and gets closer and closer to that open dot. It never equals that open dot, but it's getting closer to that open dot, and that value, the value of y at that open dot is 2. It is the limiting value. So the limit as you approach 4 from the left hand side, from the right hand side, is 2. Does a limit exist at 4? No. Let's consider another example before we move on to properties of limits. So let's take this function . Let's say that value is -1, that is -2, that's 3, that's 1, we'll call that 2, and we'll call that 3, that is also 2, we'll call that -1, and that as -3. So that is our function. We have multiple breakpoints here. So let's see and we have something like that. So as you approach -3 from the left hand side, the value of the function, the point that we hit, is 0. Excuse me, 2. So that is the open door. So we'll get 2. As you approach -3 from the right hand side, we are hitting the same point. It is still 2. So the limiting value, the limit at -3, does exist, and it is 2. But notice the function is not defined at 2. That is, it doesn't have a fixed value because of the open dot. Right? So at a point, the limit might exist, but the value of the function may not exist. In this example, it is very clear that the limit at negative 3 is 2, even though the function is not defined at negative 3. So we could look at the limit at negative 1 from the negative side. As you come from the left hand side closer to negative 1, you hit that point, so we end up getting 3. As you come from the right hand side, get closer to negative 1, you get 2. Does a limit exist at negative 1? No, because the left limit is not equal to the right limit. To negative 1. We can look at 1 as you approach 1 from the negative side. So as I get closer and closer to 1, which is right here, as I get closer to 1, the value of the function gets closer to that point right there, and let's say that value is 1. So I get 1. But as I come from the right hand side closer to negative 1, the point that I hit past this open door right there is negative 1. So from the right hand side, the limit would be negative 1, which would imply limit does not exist at x is equal to 1. If you look at 3, as you get closer to 3 along the x-axis, the function gets closer and closer to negative 2. So as x approaches 3 from the left hand side, the value of the function is negative 2. As x approaches 3 from the right hand side, the value of the function, x is approaching from the right hand side, the value of the function is still the limit of the function is still negative 2. So the right-sided limit and the left-sided limit are negative 2. So the limit at x is equal to 3 is negative 2. But something to note here. Note the value of the function is positive 2. In other words, f of 3 is actually 2. You look at that closed dot right over there, that is the value of function at x is equal to 3. So keep in mind the limit of the function needn't be the same as the value of the function. A limit might exist, but the function value may not exist. So we've demonstrated both cases in this example. Some important properties of limits. Suppose I have two functions, f of x and g of x. Now, if I have to take the limit of f of x plus or minus g of x, it would simply be equal to the limit of the first function plus or minus the limit of the second function at a added together. So the limit of the sum is the sum of limits. The limit of a product is simply the limit of the first function multiplied by the limit of the second function. So the limit of product is the product of limits. So if you have a function raised to the power n, the limit is limit x approaches a, f of x raised to the power n. So the limit just moves inside the function, then you take the power. Similarly, if you have the root of n, then the limit would simply be the nth root of n and the limit taken inside. This would only work provided that number is positive. So provided the limit is positive when n is even. So let's take two functions and let's demonstrate this quickly. So and that's 3, and let's call that value as -1. That is the first function, f of x. Let's take the second function. That is g of x. Let's call that value to be 4, and that as 1. Notice the limit does exist at x is equal to 1, and that value is 4. For f of x, on the other hand, the limit does not exist at x is equal to -1 and x is equal to 1. However, the limit at 3 is actually -1. So, for instance, suppose we want to find limit x approaches 1 f of x plus g of x, which is the limit of f of x plus the limit of g of x at 1. So the limit of f of x at 1 is dne, doesn't exist. The limit of g of x is 4 at 1. 4 plus doesn't exist, it simply does not exist. So as you can see, the limit of the sum is the sum of the limits. The limit x approaches 1, f of x times g of x, similarly, would simply be limit x approaches 1, f of x times limit x approaches 1, g of x. We know at 1 f of x doesn't have a limit. At 1 g of x has a limit of 4, so 4 times dne is still dne. There are other properties of limits that are quite important. So one of the properties is limit x approaches a f of x equals f of a if the limit of a function at a equals the value of the function at x is equal to a, then that would simply mean f of x, the function, is continuous. In other words, there are no jumps or breaks, no discontinuity. If you have two functions and you know that one function is less than or equal to the other function, and this would imply the limit of the first function at a will be less than or equal to the limit of the second function, provided the limits exist. And a very important theorem is called the squeeze theorem or the sandwich theorem. Suppose you have three functions. And we know for a fact that the limit as x approaches some number a, f of x is equal to the limit x approaches a, say h of g of x, and let's say that value is L. If f of x is less than or equal to h of x, which is less than or equal to g of x, this would imply the limit as x approaches a, h of x would simply be L. In other words, if one function is stuck or sandwiched between two functions, and if you know the limit of the two functions, then the value of the limit of the function that is stuck in between would be the same as the other two functions. To illustrate the sandwich theorem, let's take three functions. That's my first function, and the second function is that, and the third function, the dotted line, is right in the middle, something like that. So that is our point. Let's call that 1. Let's say that value is 5. We call it 5. So we have three functions. This is f of x, this is g of x, that is h of x, and you can say that h of x is squeezed between f of x and g of x. So clearly g of x is less than or equal to h of x, which is less than or equal to f of x. So h of x is getting squeezed between g of x and f of x, and we know the limit as x approaches 1, f of x is 5. The limit as x approaches 1, g of x is also 5, and since h of x is squeezed or sandwiched between f of x and g of x, limit as x approaches 1, h of x is also 5. And that's what we call the squeeze theorem. As an extension of the previous properties, limit x approaches a, if you recall, f of x raised n is simply limit x approaches a, f of x raised n. So simply put, we use this property, limit x approaches a, x is simply a, therefore limit x approaches a, x raised n is simply a raised n. And also, if you multiply a function by a constant, the limit doesn't affect the constant, so the constant would come out and you apply the limit only for the function. And these are some of the commonly used properties of limits, and limits are quite useful when we do derivatives. By all means, the definition of a derivative is based on a limit, how we get closer to a certain value. So things to keep in mind: the limit of a function at a particular point may or may not exist. The limit of a function needn't always equal the value of the function. The limit of a function may exist, but the value of a function may not exist. In other words, the function could be undefined. For a limit to exist, the right-sided limit must equal the left-sided limit at some given point A. Thank you for watching the video.